What's going on, everybody? In this video, we're going to be using derivatives to help tell us where a function is increasing or decreasing, where it's concave up, concave down, where it's got inflection points, max and mins, all that stuff. So let's get into this video. So I have the timestamps on the left if you want to jump to anything in particular here, but in this video we'll start off with an introduction here, and that's just going to give an overview of these little bits of information, what they're for, what they do, all that stuff. So we'll be getting into how to tell where a function is increasing or decreasing. We'll be getting into the first derivative test, which is going to help us find where a function has a max or a min. We'll be getting into concavity, which is basically where a function is curving up or curving down. That's concave up and concave down, respectively. And where a function has inflection points. This is where you're switching from a graph that's curving up to a graph that's curving down. Okay? And so you're just switching concavity. That's what inflection points are. And then you have the second derivative test, which is another way to tell where something has a max or a min. It's just now you're using the second derivative instead of the first derivative. And then we'll be doing a full practice problem where we're finding all of this information. Right, we're finding increasing, decreasing concavity, inflection points, max and mins, all that stuff. And we're going to find all of it and use it to help us sketch a curve. Then we're going to be given a bunch of information about a function, its derivative, its second derivative, all that. And we're going to use that information to sketch a curve. And that's another very common practice problem. It's a little bit different than this one. And as always, I have the unfinished and the finished PDFs in the description down below. Now, before we get into this video, I quickly wanted to mention my full Calc 1 course, which I'm going to have linked in the description down below. When I was in Calc 1, I would learn the topics in class and do the homework that night, but then, like most of us, I would start forgetting how to do pretty much everything within a week. Now, I don't want that to happen to you because it makes studying for tests, midterms, and finals way more stressful because you have to start studying from square one. And that's why in my full Calc 1 course, I have a bunch more practice problems for you to try. I also have full video explanations for every single problem in the course, so you don't have to waste time scratching your head. So if you're interested in that, be sure to check out the link in the description down below. Now let's get into this video. So let's start off with that introduction here, and basically what I have written here is that in order to do these different applications with calc that we're going to be doing in the future, we need the key features of graphs. We need things like increasing, decreasing, concavity, all that stuff. And so what we can do is we can use derivatives to find these key features, okay? And so here's a cool little table that I drew that talks about 4 of these different key features that we'll be talking about in this video. So the first is increasing and decreasing, right? We all know what a function that is increasing is and what a function that is decreasing looks like, right? That's self-explanatory. And what we can do is we can actually find if something's increasing or decreasing based on if the first derivative is positive or negative. That's what the increasing or decreasing test is. Think about it. If the first derivative is positive, that means that you're going upwards, right? That would make sense because think about literally any line. If you give it a positive slope, right, which correlates to its derivative, that line's going to go upwards. Versus if you give it negative slope, it's going to go downwards. And that's the same exact thing for any graph. Okay? And so that is the different idea with increasing and decreasing. We'll talk about that in the orange section, but basically that's already the concept. Then we'll talk about max and min values. And again, that's pretty self-explanatory, right? A max value's up here, min value's down here. And we can use either the first derivative or the second derivative to find these max or min values. That's what we'll talk about with the first and second derivative tests. That will be both yellow will be the first derivative test, and I think, cyan is going to be or aqua, whatever you want to call it, is the second derivative test. And so we'll talk about that there. There's different ways that we can talk about it. Like if we know something is switching from increasing to decreasing, right? We know that it's a maximum. And that's basically what the first derivative test tells us. And then the second derivative test will get into that. So then we'll also get into concavity, something that's concave up, concave down. And if something's concave up, that means it's curving upwards. Like for instance, this parabola is curving upwards, right? And so that is concave up. Okay, you also have things like concave down, and so this function is curving downwards, and so it's concave down. Right? Now that's easy to see with something like a parabola, but could you actually tell that with this guy right here, with inflection points? Right? With this guy down here, which I'll mark off where the inflection point is, it's right here. We're switching concavity. We're switching from positive, or actually in this case, we're switching from negative downward concavity, right? This thing's curving downwards. You might not be able to see it as well, but this function is, if you drew a straight line, it's actually kind of curving downwards this way, right? And so this has downward concavity at first. You can kind of think of it as this part of the parabola. And then it starts curving upwards. And so that switch off from curving downwards to upwards is called the inflection point, right? The point where that occurs. And so to find concavity, that's when you look at the second derivative. And so if it's basically like increasing or decreasing. If the concavity is, or if the second derivative is positive, we know we're concave up. If the second derivative is negative, we know we're concave down. And then if we're switching from, a second derivative that's going from positive to negative or negative to positive, that's when we know we're switching concavity. That's inflection point, right? And so that's all what we're going to be talking about, basically. That's your introduction. So now we'll get into increasing and decreasing, right? And it's going to be basically exactly what I just talked about. If the first derivative is greater than 0, then we know it's increasing. If it's less than 0, we know it's decreasing, right? And if that is strange to you for any reason, replace derivative with slope. Think about it this way. If the slope is greater than 0, it's increasing. If the slope is less than 0, it's decreasing, right? Derivative and slope, same idea, right? Same rate of change idea. But yeah, that's the idea. So I'll actually draw out those tangent lines on this graph. To do that, I'll white the entire thing out, and then I'll draw the tangent lines in orange. So let's draw a tangent line to the point, or to the graph right here. Okay, that's good enough. And here you could agree with me that the f prime of x, right, the derivative of f is going to be greater than 0. That would make sense, right? On the opposite side, you would have a first derivative that is negative. And I'll move this a little closer to the curve. There you go. Here, the first derivative would be less than 0. Okay? And, right, that would make sense because it's moving downwards now. But how do we get from something that's greater than 0 to something that's less than 0? Well, we'd have to cross 0, right? And that would be at the maximum. And so that's going to key us in a little bit later for the first derivative test. So let's do an example with that. And so in this example, we're going to determine where this function, f of x, is increasing and where it is decreasing. This is going to take a little bit of elbow grease to get right, but it's not that bad, I promise. So what we're going to do first is we're going to take that derivative, because the derivative is the key to everything here. The derivative here would be just a bunch of power rule, 12x cubed minus 12x squared minus 24x, and the derivative of a constant is 0. So now we have the derivative. What do we do with it? Well, it's going to be really good for us if we find our critical points, because if we find our critical points, right, where the derivative is 0, then what's going to happen is we'll have all the points, right? Let's say these are our critical points here. These are the only x values where we can have a function that switches from increasing to decreasing. Remember what I just talked about with you. When we're switching from increasing to decreasing, we have to go through 0. Right? We have to go through 0 or a point where the function is undefined. Okay, and that's like, you think about for like the the absolute value of x, right? We're going from decreasing to increasing, but here the derivative is undefined. So that's what I'm talking about there. But mainly it's 0 is what we're talking about. And so if we find our critical points, that's going to be key for us, and I'll talk about a little bit more about why after we find them. So we have 0 here is going to be equal to, let's factor an x out, and we can also just divide 12s away. So maybe that's a smarter option first, actually. Let's do that first. We'll write this as x cubed minus x squared minus 2x, and then we'll factor our x out. Then we just got to factor this. And the question is, what are two numbers that add to be -1 and multiply to be -2? Well, that's going to be -2 and +1. Okay? And now you can see that your critical numbers are going to be x equals 0, x equals 2, x equals -1. Okay? Great. And these are important. So now what we do is we can make this thing called a sign chart. Okay, we're going to make a little thing called a sign chart. Why do I call it a sign chart? I call it a sign chart because it's basically a number line, and it's going to have your critical points on it. So we're going to have 0, we're going to have 2, and we're going to have -1. It's not going to be like, the regular number line spacing. You don't have to do that, because if you get a critical point that's -10, then you'd be shoving these things right next to each other, and that would be just, terrible to look at. But having them in order is key, right? So -1 goes first, and then 0, and then 2. So the sign chart is called the sign chart because you're going to put different signs here, positive or negative. And that is going to be whether, from 1 to 0, this thing is got negative slope. From 0 to 2 maybe has positive slope, and that's how we mark that. But how do we find all that stuff? Well, what we're going to do is use a test point. We're going to plug, something out here. We'll plug a point in right for our derivative function. We'll plug an x value in, something out there, because we know that if we plug in any x value out here, that this thing is either going to be negative or it's going to be positive. And if it's negative, it's decreasing. And if it's positive, it's increasing. And so that's all we're going to be doing here. So we're going to start off here with our test points. I think the first test point that we'll use out here, I think it's best to use just -2. Right, you don't want something too big. I would go the next number over. That's going to be -2. So let's plug that in. We get that f prime of -2 is 12 times -2 cubed. It's going to get a little gross here, but I'll give you all the numbers. Or you can use your calculator. Okay, that's f prime of 2. And if you do that math out, you're going to get -96. That's a negative number. That's the important part. That's what we need to pull out of that. If it's a negative number, we're going to put a negative sign right here. Then we got to next pick a number that's in between -1 and 0. I'm going to pick -1/2. So f prime of -1/2. Now we're just going to put a -1/2 everywhere that we see an x in this function up here, right, in the derivative. So we're going to do 12 times -1/2 cubed minus 12 times -1/2 squared minus 24 times -1/2. All right, and in doing all that out, you're going to, I didn't actually go out and I should have put all that into calculator, but I didn't. Here's what I just simplified it a little bit. So, alpha here, you get a negative 1 over 8. Here you'd get a 1/4. And here you just have a negative 1/2, right? So if you just write all these, I'll put it down here. If you do all that, you get this thing. Okay, and the reason why I didn't simplify it is because let's say that you don't have a calculator here. You don't need to go out and find common denominators here, and you don't have to go through all that work. Honestly, if you can just have a good idea of whether this thing is going to be positive or negative, you're fine. That's all you need. And here we can see that this thing is definitely going to be positive. How do I know that? Well, because this is like a negative 1 point something, okay? This is a negative 3. That's like negative 4 together, right? And 12 is much bigger than that. So I know this thing's going to be positive. And so now we're going to put a plus in between here. Then we need to pick a number in between 0 and 2, and I think 1 is going to be the nicest number to pick there. And so computing f prime of 1, we're going to get 12 times 1 cubed minus 12 times 1 squared minus 24 times 1. And that right there is going to be 12 minus 12 minus 24, which is definitely negative. Okay, because the 12 and the 12s cancel off and you're just left with negative 24. So then we're going to put a minus sign in between here. And then the last category that we need to fill is a number that's in between 2 and infinity. And that we can just use 3, right? The next highest number up. And so we do f prime of 3. We know that that is going to involve some more plugging into our function. And these numbers are going to be pretty disgusting here. When I did this, I got 324 minus 108 minus 72. And from there, I already knew that this thing was going to be positive. Okay? So, yeah, just like a little bit of lazy calculator work, I guess. But it is what it is. It is what it is. So yeah, that's going to be positive. So now we have where this thing is decreasing and where this thing is increasing. Right? It's all based on where that first derivative is positive or negative. So if we want to write this out as our answer, we can write increasing, decreasing. And then we're going to write an interval. We'll write this in interval notation, if you remember that. Right, increasing from, we know it's increasing from here and here. Oh, not here. There we go. And so that is in between negative 1 and 0. We don't include the endpoints because this is where it's neither increasing nor decreasing. And then we're putting that, that's like an and, right, to infinity. And then decreasing, it's going to be from negative infinity to negative 1, right? That's this point right here, or this area. And then from 0 to 2 as well. And that right there is our answer for the orange section problem. Okay, so again, it involved taking our derivative, right? Finding the critical points by setting it equal to 0, and then doing a sign chart. And to do that sign chart, right, part of that was these test points. This is probably the most amount of test points that you'd have to do. I think this is probably a longer problem as far as, you know, the test points go, because there's 4 of them. Usually it's like 2 or 3, mainly 3. So now let's move on to this first derivative test. Okay, so we've been talking about how critical numbers are where your derivative is 0 or it's undefined, right? But let's focus on the equals 0 part. Okay, now critical numbers, they have a possibility of being extreme values, meaning they have a possibility of becoming, or of being max or mins, Okay, but how do we know whether a critical number is a max or a min? We don't have a test for that yet. Okay, the practice that we've done in past videos is to find these absolute values, these absolute max and mins, by having some graph on your interval, finding the critical points, and then just at each critical point, right? We don't even discriminate between these critical points. We just go and we find the y values at each critical point, and we take the lowest, we take the highest, and that's our absolute max and min. So now we're actually going to have a test so we can figure out whether something is like a local max or a local min. Okay, that is the first derivative test, and then later we'll also talk about the second derivative test. That's the same thing. So here we go. Here I say we can come up with a test for this, okay? And so around any critical number that you see, any critical number, there's 4 things that could happen. Okay, the first thing that could happen is that you could get a graph that looks like this. Okay, and actually I'll make that a little bit bigger. You could get a graph that looks like this, right, where these guys are your critical numbers. You could get a graph that looks like this. This is a critical number. You could get a graph that looks like this. Oh, I always mess up with this one. There. Where this is a critical number. Okay? So, here's the differences. Here you have a critical number, right? You know your slope is 0, right? Your slope is 0 at all these points. But what happens around them changes. On the left side, in this first picture, we have the slope that is negative and then it's positive. And in this case, we do end up with an extrema. We end up with a minimum here, right? When it goes from negative to positive. When it goes from positive to negative, on the other hand, this right here is going to give you a maximum. Okay? And then you have other cases where this doesn't happen. When you don't switch from positive to negative, when you just go from positive back to positive again, right? In this case, you went from positive, you've decreased to 0, and then you go positive again. Okay? This right here is not a max or a min. So you've kept the same sign for your derivative. And then here, this is the same thing, but now you're going from negative to back to negative. And so this is another place where you don't get a max or a min. So the only time that you get a max or a min is when you switch from negative to positive or from positive to negative. And so that's going to be the first derivative test. Okay? That's how we know whether we have a max or a min. Here's that written out just a little more formally, I guess. If f prime changes from positive to negative, it's got a maximum. If f prime changes from negative to positive, it's got a minimum. If it doesn't change, it does not have a max or a min. That's the first derivative test. Okay? Cool. So then let's use that first derivative test and actually, well, do a problem. This problem says to determine the local max and min values of the function below from 0 to 2 pi. That function below is f of x, which is x plus 2 sine x. So for this, what are we going to do? Well, it's going to be more or less the same process as before. We're going to do the exact same thing as if we were finding whether something was increasing or decreasing. We're going to take a derivative, we're going to set it equal to 0, find our critical points, and from there we're going to do a sign chart. We're going to see where it's, where it's increasing, where it's decreasing, and if we know that, we know where it's switching over from increasing to decreasing, now we know where our max and our mins are. So same exact process, but now we're just taking different information, right? Instead of increasing, decreasing, we're taking max and mins. But I guess in order to do that anyway, we need the increasing, decreasing. So, all right, let's start off by taking that derivative. I wasn't lying. Okay, when we take this derivative, we're going to get 1 from the x, and then from the 2 sine x, that goes into a plus 2 cosine x. We're going to set that equal to 0, and then look, we have a trig equation here. Probably haven't done one of these in a while. We're going to subtract 1 on both sides here. You can see the negative 1/2 coming maybe. Divide by 2 on both sides. We're going to get that negative 1/2 is equal to cosine of x. Now, where the heck is cosine going to be negative 1/2? Well, first off, we know it's negative, and so that already narrows it down for quadrants. Okay? And so we know that either you can say all students take calc or some other things that I probably shouldn't say in this video to remember this mnemonic, but yeah, that's exactly it. So we know that all trig functions are positive in the first quadrant, only sine's positive in the second, tangent's positive in the third, and cosine's positive in the fourth. So we know that the two quadrants where this x could end up in is going to be sine, or the second quadrant and the third quadrant, because cosine's not positive here. Okay? So sadly, we're going to be doing our answers here in radians. I hate radians. They're just a little bit messy, you know, compared to like nice easy degrees, but it's all good. It's all good. Let's do it. We know that cosine of 60, or we could say cosine of pi over 3, right? 180 divided by 3 is 1/2. But that's in the first quadrant. How do we make that a second quadrant angle? Well, we subtract it from pi, right? We subtract it from 180. Okay? That's how you get the first quadrant equivalent. You do 180 minus theta here, you do 180 plus theta here, and you do 360 minus theta here. Okay, and so we got to do pi minus that angle to get the first quadrant equivalent, or the second quadrant equivalent for that angle, and then this is going to be one of the values for x. Then you also have pi plus pi over 3. That's 180 plus theta, right? We're doing 180 plus pi over 3. And that's going to give you 4 pi over 3. That right there is the other x value. And so now we have our solutions to this guy. X is, well, I'll even just skirt the x on in here. Perfect. And so now you have your two critical points. So now we are going to do our sine chart. So I'm going to bring all of this up here, make a big line up here, and we're going to do our old sine chart. And we're going to put on our number line 2 pi over 3 and 4 pi over 3. Okay, and remember, this is closed off now. We're on an interval, so we're going to be in between 0 and 2 pi. And no, we're not going to be testing our endpoints for if they are max or mins, or if, you know, which they are. Because when we're talking about local max and mins, we don't really include the endpoints. I know we did when we were talking about like absolute stuff, but technically, and I guess this is kind of argued about by some people, don't worry about it though. The endpoints are going to be not considered at all when talking about local maxes or mins. Okay, they don't count because you don't know what's on the other side of that endpoint, and so you're not able to call it something that's local, right? You need, for something to be called local, it needs to be a maximum for things around it. But if you just cut it off here and you don't know what goes on over here, you can't call it a max because you don't know what's going on over here, right? You don't know if it's like this, and in the case, this is not a max. Okay, so that is basically why we don't include the endpoints at all. Okay, so we know that we need, okay, we know that we need something in here, something in here, and something in here. We need 3 test points. The test points that I volunteer for tribute are going to be, well, something in between 0 and 120. That's what this is, right? I would say just go with pi over 3. Right, because we know what the cosine of 60 is. You could also do pi over 2. That's probably even easier. Actually, yeah, let's do pi over 2. Right, that's in between 0 and 2 pi over 3. And so we have 1 plus 2, and this is prime. 1 plus 2 cosine of pi over 2. Cosine of 90 is going to be 0, and so this is just 1. And so that's positive. Now something that's in between 2 pi over 3 and 4 pi over 3, well, that could be 3 pi over 3, and that's just pi. So f prime of pi, plug that guy in, you get 1 plus 2 cosine. Dogs, come on, I'm recording a video. 1 plus 2 cosine of pi is going to be 1 minus 2, because cosine of pi is negative 1. And so right here, we're going to get negative 1. That's negative. Then here, we can, I mean, if you really think about it, this guy's 240 degrees. And so we can use 270 degrees, or 3 pi over 2. Okay? And so we can do that just by going 1 plus 2 cosine of 3 pi over 2. And we know that is also going to be 0. So we get just 1 here, that's positive. So negative, positive. Okay? And, just, if you're having trouble doing this degrees radians conversion, just know I did do, it would probably take me a little bit longer if I was doing it now, but I like to do it in both degrees and radians a little bit, because radians is what you want to be writing your answers in, right? You want to be doing like f prime of, and you don't want to be plugging in, like 90 degrees into the argument of your function. You want to be plugging in pi over 2. And so what I do, though, just so I can understand where these angles actually are, is I convert them to degrees. I think about that, like, okay, 2 pi over 3 is 120. And from that, I know that, okay, I can use 90 because that's on one side of it. I can use 180, that's on the other side of it, right? And so that gets the whole flow going for me. But, yeah. All right, so we know where it's increasing and decreasing now, right? It's increasing here and here, it's decreasing here. And so now we know whether there is max or min. Okay, we know there's going to be, since it's increasing here, decreasing here, there's going to be a maximum here. It's decreasing here, increasing here, that's going to be a minimum. And so we should find those values before we write our answer. So f of 2 pi over 3. And this is going to be the function up here. That's x plus 2 sine x. And that is going to be 2 pi over 3 plus 2 times sine of 2 pi over 3. And if you write this out as a decimal, you round it, it's going to be about 3.83. Okay? And then, I'll make this decimal a little bit bigger. And then you have f of 4 pi over 3, right, the minimum, and that's going to be 4 pi over 3 plus sine of 2 sine of 4 pi over 3. And that's roughly negative, not negative, it's going to be just 2.46. Cool. And so we can even write, this is a local min, and label the other guy as a local max. Okay, and then we circle these guys up. So really, that is all that goes on in a problem like this. Okay, I know it looks like a lot, but really, we take our derivative, we set it equal to 0, find our critical points. That's pretty much what we do in every single one of these problems, right? We start off by taking a derivative, setting it equal to 0, finding the critical points. Here it was a little bit more messy because we had a trig equation, but sometimes that is going to happen. But then we were able to find our critical points still, and from that we used a sign chart, we plugged in test points, and, well, we got our x value for our local max, and so we can, from there, find our y value for that local max, right? And then we did that again for the local min. How do we know whether local max or local mins? Well, we just look at our sign chart. If we're going from positive to negative slope, then we know we have a max. And if you go from negative to positive, we know we have a minimum. Okay? Same thing every time. All right? Great. So now we'll talk a little bit about concavity and inflection points. And the idea is, it's great to be able to tell whether a function's increasing or decreasing to find the max or mins, but it doesn't really give you a good idea of how that function is curving. Right? That's what concavity does. It tells you whether a function is curving upwards or it's curving downwards. And so look right here, I have two examples. Here's a straight line. If you're curving upwards, you deviate from this line and look something like that. That's what concave up is. Okay, and I'll write that here. That's concave up. Then if you are curving away from the line this way, that's concave down. And if you're ever not sure, then draw a straight line next to your curve, and that'll tell you exactly whether, if it's above the curve, it's concave up. If it's below the curve, it's concave down. Okay? Same thing when you have a line that's going downwards. Here, if we curve away from the line downwards, right? We're curving downwards. That is concave down. Here, though, if we deviate the other way, that's concave up, right? We're still moving upwards, and eventually this will turn into something that's increasing, right? So it's a little hard to see, but hopefully you can see how this is, instead of decreasing, right, it's starting to decrease less and less and less. It's essentially acceleration in a way. If you think about a distance versus time graph from physics, right, telling you how far you've gone in a specific amount of time, the slope of this graph is velocity, right? And if you're increasing your distance at a constant rate, right, if your slope is constant, then you have a constant velocity. But if you start curving upwards, now you're speeding up. You're increasing that velocity. And if you increase your velocity, you're accelerating, right? If you go from 30 miles an hour in a car, or if you use any other units, sorry, if you speed up to 40 miles an hour, you have to accelerate to get from 30 to 40. Okay, that's exactly what this is. Okay, so a good way to think about it is with a distance time graph. But yeah, so here right, so here I have the concavity test and inflection points, and here's where we will really get into it here. So the concavity test is the exact same as the increasing decreasing test, except for now we are dealing with second derivative instead of first derivative. Okay, so if you know the increasing decreasing test, you know the concavity test. If the second derivative is positive, concave up. If second derivative is negative, concave down. That's it. Now, inflection points are the exact same thing as like maxes and mins. Okay, and so if your second derivative crosses 0, you know that you could possibly have an inflection point. It doesn't mean that you do, because you have to change concavity from up to down or down to up to actually have an inflection point. Okay, to actually have one of those points, like in y equals x cubed. That's the best example that I have of what an inflection point looks like. When you're at negative x values for y equals x cubed, you are dealing with, and I'll even graph it here. For y equals x cubed, just graph that here. This is negative concavity. And then you switch over at 0. This is an inflection point, right? You're switching over to positive concavity. Or so I always call it positive concavity. Concave up, right? You're switching from concave down to concave up. Okay? That is what an inflection point is. Okay? So that is it for that section. Now we're going to move on to the second derivative test. And this is another way of finding your local max and mins. Okay? It might seem like, oh, since first derivative test was for your max and mins, so the second derivative test would be for your inflection points, right? The second derivative equivalent of a max or a min. But no, that's not what the second derivative test does. It's another way of finding your max or mins. And it's a little bit quicker if you already have your second derivative calculated, but you haven't done any of the increasing, decreasing stuff, right? If you don't have your sign chart done, if you don't have any of that stuff, and you have your second derivative calculated, it's actually a lot quicker just to use the second derivative test to figure out whether you have a max or a min. So if I just cut to the chase here, if something's concave up, right, if you find out that you have a critical point, right, here's a critical point, and you know that it's concave up, right, you know that the second derivative is positive at this point, that means that this thing is a minimum. Right, you can't have something that's concave down and have a critical point here and it be a minimum. That doesn't make sense. Okay, so that right there is basically what the second derivative test entails. That's all it is. If you know that you're concave down at this point, at this critical point, you know that you have a max. Okay? So instead of having to plug in test points on both sides, with the second derivative test, all you need to do is just plug in the singular point, right, into the second derivative. Now again, you should have that second derivative done, and sometimes it's even hard to take that second derivative in the first place. So, you know, it generally ends up being the same amount of steps both ways, but sometimes one is a lot nicer than the other to deal with. So there's that. So here's the second derivative test in all its glory. Basically, again, if you have a critical point and your second derivative is greater than 0, that's a min, right? This is concave up. Think about concave up being a upward facing parabola. There you'd have a min, not a max. That's how I would think about it and differentiate, because it's going to take a while to get this into your head. There's a lot of different informations going on in this video. So here, if you have a critical point and you have a second derivative that's less than 0, or you're concave down, that's a local max. Okay? So, same idea, and if this was bugging anybody, I'll switch these guys to blue. I don't know why I missed that. So, there you go. Now it's not going to bug you anymore. And then also, if you have a critical point and you have your second derivative being 0, you don't know. So the second derivative test is, it can fail in that sense, and you'd have to move on, and I would then move on to the first derivative test and just go with the flow there. There's times where if you get your second derivative being 0, you don't know. We talked about it being positive or negative, but we don't know what happens at a possible inflection point, right? We don't know if the second derivative is 0, we don't know for sure if it's an inflection point, but you get my drift. So now let's move on to the second to last thing we'll be talking about in this video, and that's a full practice problem with all this derivative information. Okay, it's quite the problem. It seems like, you know, it's this nice little harmless polynomial, but honestly, like, I hate these types of problems. You have to find so many different things. It's always to like part j1/2, and that's annoying. But we're gonna get through it. Okay. Don't let my sourpuss attitude ruin this. This is a great experience for you. Totally. So, A is giving us is telling us to find the intervals on which g is increasing or decreasing. And to do that, to even start off with that, that's going to be a great opportunity to, you know, take our first derivative, right? Take our first derivative, set it equal to 0, find the critical points, sign chart, and there you go, right? And then you'll notice that I have concave up coming right after increasing, decreasing, and not maximum and minimum, because in this case, I'm going to have you use the second derivative test, possibly. You know, maybe that'll be a good thing for us to do. So we'll see when we get there. And then at the very end, we're going to use that information to do a sketch. And the sketches can definitely seem scary at first, and they were definitely hard for me at first. But after some time and after some practice, it's going to be a lot easier to sketch these graphs. So let's start off here taking our derivative. G prime of x is going to be 4x to the third power minus 12x squared. And we know that we're going to set this equal to 0. Okay? Now, to do that, to start solving for x here, we can get rid of those. We can take out a 4 here and write this as x cubed minus 3x squared. And then from there, we can take out an x squared from both of these pieces. And voila, we have our critical numbers of x equals 0 and x equals 3. Cool. So now that we have the critical numbers, we can plug that into a sign chart. Okay. And so we're writing our number line here. We got 0, we got 3. And so we'll plug in, I think, -1, 1, and 4. Right, those will probably be good numbers to plug in here. So plugging in -1 to the derivative, right? We plug into the derivative because the derivative either has to be positive or negative, right? Not the actual original function. So for the derivative here, plugging in, we're just going to get 4 times -1 cubed minus 12 times -1 squared. And that right there is going to be a -4 minus 12, that's -16, that's negative. So we know that everything, any point that we try from -infinity to 0 is going to be negative. Well, it's going to give you a negative derivative. Okay? Then we can do g prime of 1. Right, that's the test point we'll use for this space. And that's going to be 4 times 1 cubed minus 12 times 1 squared. And that's 4 minus 12. And again, we get something that's negative. Okay? So we put another minus sign there. Now notice you would expect there to be a plus sign here. And some people, I remember some people in my calc class at the time, they would just go through and they would just do minus and they would assume that the next would be a plus and then minus a plus. No, that's not how that works always, because here we're going from decreasing to decreasing again. And so we don't get a max or a min, and so their entire answer is screwed up because they wanted to be lazy. Good times. So anyways, g prime of 4, we're just going to plug in 4 for x. And here we get something that is going to be like 256 minus 192. Right, this is definitely going to be positive. And so finally we get something that's positive. So here's our sign chart. We can already tell where it is increasing or decreasing. So we'll write that here. It's increasing from 3 to infinity. Remember, we don't include the endpoints. And it's decreasing from -infinity to 0. We don't include 0, right? So we got to stop here. We're not going to go from -infinity to 3. And then we're going to go from 0 to 3. And right there, that's the answer to part A. Okay? So let's move on to part B. Part B is asking us to find where g is concave up and concave down. So to do that, we'll need to take another derivative. We'll take a derivative of the derivative, a double derivative, which will be g double prime of x. And that is going to be 12x squared minus 24x. Okay? So how do we do this? Well, we can set this thing equal to 0, And in doing that, we can just divide each side by 12 and get rid of the big problem here, which is we have some big numbers over here. So we get x squared minus 2x. And just finding our critical numbers here, we can get 0 is equal to x times x minus 2. We get x is equal to 0, x is equal to 2. Okay? And that's cool. All right, that's cool. That's our kind of like our second derivative critical numbers, right? These are the possible places where we could end up getting an inflection point, okay? But at least we'll be able to tell at this point where we are concave up and concave down. So here's 0 and 2. Let's pick some test points. We're going to need another 3 test points. I like -1, 1, and 3. Right? Those will be the easiest. So g double prime of -1 is going to be 12 times -1 squared minus 24 times -1. That's going to be a 12 plus 24 is 36. That's positive. Next, we're going to plug in 1 for that middle test point. Right? These test points get old after a while. And this is going to be -12. Right? You got a 12 minus 24. So negative here. Then we do g double prime of 3 for that final test point. That's 12 times 3 squared minus 24 times 3. Right? 12 times 9, I believe, is 108. Well, actually, I realized the calculator's been sitting next to me this entire time. And then 24 times 3 is 72. And so we get, this is 36. Okay. And that's cool. So this is positive. Okay. And so now we can already say where this thing's concave up, concave down. And we can also say where our inflection points are. First off, we know this thing's only concave down between 0 and 2. Right? Again, we're not going to include our endpoints here because, well, at 0 and 2, we don't have a second derivative being negative or positive. It's 0. Right? That was the whole point of finding this stuff in the first place. Concave up is going to be from -infinity to 0. And from 2 to infinity. Okay? And we'll circle that. So now let's move on to part C, which is just to find the inflection points. And now from this sign chart, from the second derivative sign chart, we're already going to know where our inflection points are, right? Where we're switching our concavity from going concave up to concave down, or from concave down to concave up. We're switching our concavity at both x equals 0 and x equals 2. And so we know those are the x coordinates for our inflection points. So I'll write IP, x equals 0, and x equals 2. But for the purposes of what we're going to do later, right, we're going to use this information to sketch the graph, right? We're trying to find points. We're not just trying to find x values. We need to find the y values that go with these on the regular graph of g. Okay? It's going to help us to graph it because we'll be able to locate exactly where on, x equals 2 or x equals 0 that inflection point is. Right? And so it's just going to help us graph it a lot more. So, let's grab that g function. Where's that at? Here we go. So we're going to grab that, we copy it, paste it, and so we're going to get that g of 0 is, you can see these are just x's, right? So we're going to get 0 to the 4th, minus 4 is 0 to the 3rd power, right? This is just going to be 0. And then g of 2 is going to be a little more complicated than that just because we aren't dealing with zeros, but still not going to be that bad. We get 2 to the 4th power, which is 16, minus a 4 times 2 to the 3rd. 2 to the 3rd is 8. 8 times 4 is 32. And so we're going to get that g of 2 is -16. And so our inflection points, if we would just want to write them out a little cleaner, we can write these as g of 0 is 0 and g of 2 is negative 16. Okay, and that'll do it for part C. Okay, so now moving on to part D, usually you'd see, finding maximum and minimum values, you'd see that in between parts A and B, right? And that would just be something you do right after you talk about where it's increasing or decreasing. The reason why I moved it down here is because at this point, we've already done some work with second derivatives in part B and C. And so I wanted to give you the option to use the second derivative test to find your maximum and minimum values. Now, the second derivative test is not always going to work. And so we'll see that actually in this problem, an example of where the second derivative test doesn't work. But when would the second derivative test actually be nice to use? And I think that's what you'd actually want to know about this, right? You'd be like, well, if I've already calculated some first derivative stuff, I know where, I have this sign chart. I already know where the max and mins occur. And if there are max or mins, why do I need a second derivative test? Well, imagine that this problem didn't ask for anything about increasing, decreasing. So you wouldn't have ever had to make this sign chart. All you would have had to do is take a first derivative, because that'll get you to this other stuff, which let's say it did ask, right? Let's say it asked for concave up, concave down, and points of inflection. Well, then all you would have done is take a first derivative, and then take a derivative of that guy to get your second derivative. Okay? And so at this point, you don't have to go through all the work of getting that sign chart from the first derivative and then plugging in a bunch of test points. Because since you already have that second derivative, all you have to do is plug in points. Okay? And that's exactly what we'll do here. So remember, we're just going to take those critical points and plug them into our second derivative. And then we'll talk about it when we get done with that. So our critical points are 0 and 3. So plugging in the 0 into our second derivative, right? We know our second derivative is, sorry to scroll so much, 12x squared minus 24x. So 12x squared minus 24x. Plug in that 0 in both of those places, and you're just going to get 0. And this is where the second derivative test is inconclusive, right? We're looking for positive or negative numbers, and here we just get a 0. So that's neither positive nor negative. And so what this means is, well, if it was positive, we know that we're concave up, right? If our second derivative was positive, we'd be concave up. We know we have a min. And so if we were negative, if our second derivative was negative, we'd have a max. We'd know we're concave down. But if it's 0, we don't know. It's inconclusive. It doesn't mean that there's neither a max or a min, but we don't know if there is a max or a min. And so what we would need to do is look at the first derivative test, and we would actually need to plug in points around 0. Okay? So in this case, it doesn't really work out too well. So we could just say, from this data up here, right, from our sign chart, we know that there's neither going to be a max nor a min here, because we're going from decreasing slope to more decreasing slope. And that doesn't give you a max or a min. Whereas with 3 here, we have decreasing slope followed by increasing slope. So we know there's going to be a min. And so you'll see that here when we plug into the second derivative. G double prime of 3 is going to be 12 times 3 squared minus 24 times 3. Plugging in there, you're going to get 12 times a 9, which is 108. And then you have minus 24 times 3, which is 72. Okay? And if you do a little bit of subtraction here, you are going to get 36. Okay? This is a positive number. That's all we really care about. Is it positive or negative, right? Even from here, you don't even have to do that subtraction if you don't want to, because you already see that it's going to be positive, right? And so since it's positive, we know we're concave up, and that means we're dealing with a min. And again, that's exactly what we were expecting. Okay? So there's another way to determine whether you have a max or a min if you haven't already done all that sign chart stuff with the first derivative. So now that we know that there's neither a max nor a min at 0, and there definitely is a min at 3, what we can do is just find where that min value is by plugging in 3 to the original function, not the second derivative. I'm talking about the original function. That'll give us the y value. And if we do that, remember what the original function was x to the 4th minus 4x to the 3rd power. And so we get this to the 4th minus 4 times this to the 3rd power. Okay? And, well, 3 to the 4th is 81. Right? 3 times 3 is 9, right? That's 3 squared. And multiply that by another 3, you get 27. Multiply by another 3, you get 81. Then you have minus 4 times 27. Okay? And then 27 times 4, we'll do that out real quick. It's going to be 28 there. Then you get a 108. Doing this subtraction, you're going to get negative 27. Okay? Cool. And that right there is your min. So you can say that g of 3 equals negative 27 is a min. Now part E is asking you to sketch this graph of g. And how you should do that, right? You can organize all your information first off if you want. It'd probably be the most beneficial if you put all like the first derivative stuff on one side and the second derivative stuff on the other. That's just like a really nice way of organizing things. But what I would do here is I would start off by just writing down the important x values, right? I would just plot out all the important x values on this graph that you see here. Okay, we see a 3, a 0, we see a 2, and so we know that those 3 are the important x values where things are happening to this graph, right? So we can mark out 1, 2, 3. Okay? Now, we can also then mark out our minimum point and our inflection points. So I'll do that now. Can mark out 0. Right, that's an inflection point. And then we have a min at negative 27. Okay, that's going to be way down here. And that's a minimum point. Okay. And we'll call that, we can just say right negative 27 there. Okay, and then we have a inflection point at negative 16. So we'll put that like right here. Okay. And so here's where we know important things are happening, right? We have our points plotted out, and we have all the x values that we need. Okay? And so now what we're going to do is we're going to start, and we're going to basically segment this thing. To make it the least confusing as possible, I'm actually going to erase 1. And now we see this thing is divided into 4 sections, right? Actually, we have 5 sections here, I think. Yeah. 1, 2, 3, 4. Yeah, 4. Okay, 4, not 5. So first off, from negative infinity to 0, this graph is going to be doing the same thing, right? There's no changing in increasing, decreasing. There's no changing in concavity. It's just doing the same thing. And then you have another zone from 0 to 2, where things are just doing the same thing, right? But they're doing something different than they were over here. That's why it's a different section. And then from 2 to 3, there's another section, and then from 3 to infinity, there's another section. Remember, the only reason why I divided this up is I just used all the x values that I saw, right? And they were all either 0, 2, or 3. So that's where I know I'm either changing increasing, decreasing, or I'm changing from concave up to concave down, whatever. So first off, in this negative infinity to 0 zone, what's happening? First off, we can ask about first derivatives. Am I increasing or decreasing? Well, we know I'm decreasing. Okay, so I know I'm coming down to it. Am I concave up or concave down though? And here it says I'm concave up. And so I would imagine that it would look something like this. right? This is concave up, right? It looks like a parabola, upwards parabola, right? It's curving upwards, and it's decreasing. So we're all good there. Now we know there's an inflection point at this point right here, so we know we're changing concavity. We're going downwards now. And so you can even see here we're going to be concave down now from 0 to 2, and we're still going to be decreasing. And so hopefully you start to see how all these things come together. The graph kind of acts exactly how you would expect it to. Right? And so that's your little concave down. It kind of looks like y equals x cubed in a way. All right? Cool. So now we're going to look at from 2 to 3. And we know we got to get to this point, and we know that 2 is an inflection point. So we know we're changing concavity, and to get to this point, we'd have to be decreasing, and it even shows that here. So we do that. You see how we've changed concavity each time. Here we were curving upwards, here we're curving downwards, and here we're curving upwards again. Right? If you don't know whether you're curving downwards or upwards, keep curving, and you'll be able to tell. Okay? Cool. And so then the last step here is to go from 3 to infinity, and here we know we're increasing from 3 to infinity. So it's going to be something like this. But is this line going to be curving up or curving downwards? I guess it really wouldn't make too much sense for it to be curving downwards. But, you know, there's things that could happen, I guess. But here we know we're concave up from 2 to infinity. So we're going to keep going concave up here, and we're just going to keep increasing. And there you go, that's your graph. So it really isn't that bad to be graphing something like this, right? You have your first derivative stuff here that you can take. You have your second derivative stuff here that you can take. And, well, yeah, you just divide it into those sections. All right. Moving on to the last piece here. Now, we're already given all this information, right? But we're given it in form of not like we were given here, right? Where, well, we weren't given this, we found it, but we organized it into where it was increasing, decreasing, concave up, concave down, inflection points, maxes and mins. We're going to have to do all that organization for this right here, but it's going to be a lot quicker than it was for the last problem because, well, we actually have this information. Okay, so we're going to do the exact same thing. Let's just start off here. We know that if the derivatives here, right, these are the derivatives of your function at different x values, we know they're all 0. So all these guys are critical numbers. This is where your slope is going to be 0. And these could possibly be maxes or mins. We don't know. We need to look at how the first derivative changes. And it's usually given in order here. First derivatives here, second derivatives here, right? You have where your first derivative is greater than 0 and less than 0, and you have where your second derivative is greater than 0 and where it's less than 0. So we can see right here from part 2 here that it's increasing from negative infinity to 0, right? Because it's where x is less than 0, and from 2 to 4. From this guy, we can see it's decreasing from 0 to 2, and from 4 to infinity, right? Because it's x, all x's that are greater than 4. Now from the second derivative, we can see where it's concave up, and it's going to be concave up from just 1 to 3. But all the other times, it's going to be concave down, and that's going to be from negative infinity to 1, and from 3 to infinity. Okay? Now, we have all the increasing, decreasing, the concavity organized, that's good, but again, let's get back to our critical points. For our critical points, are these all maxes or mins? Well, looking at where these things are increasing, decreasing, we know we switch over at 0 from increasing to decreasing. So we know we have a max at x equals 0. We know that we're switching from decreasing to increasing at x equals 2, and that's a min. Lastly, we're switching from increasing to decreasing at x equals 4, And so that's a max. And now we have all our information. Okay? So we just gotta really do the exact same thing as what we did in the last problem. So let's copy all this information. We'll get it put down here next to our graph. Make it a little bit smaller, I guess. And we'll write out our graph. Leave a lot of space for this graph. Okay? So, again, look at this. What are all the numbers you see? We see 0, we see 2, 4, 1, 3. Okay, that looks about it. So we're going to plot out 0, 1. It's a little too close. 1, 2, 3, and I'll extend this a little bit. 4. Okay, it looks like we're primarily focusing this graph on the positive side. That's where all the good stuff is happening. Cool. So now we have a bunch of different sections. We have from negative infinity to 0. We have from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to infinity. And so that is 6 different sections. But it's not going to be terrible here, I promise, right? It's not too bad. Let's start off and let's just look at negative infinity to 0. Look at the first section. Now from negative infinity to 0, we know that we're concave down. Okay, so it's going to look something like this, or it's going to look something like this, right? We know that's right because that makes a parabola. And we know that we're increasing though. So that's going to be this one. So we're going to be coming up from the bottom. We can come right to 0 if you want. I think that's just we don't have any actual points here, so I'm just going to come up to that. And then what happens at this x equals 0 line? Well, next we need to look at 0 to 1. And from 0 to 1, we're still concave down. Okay, so we're still curving down, but now we are going to be decreasing. Okay, so we'll turn around here, come to 1, still concave down, but now we're switching concavity, finally. We're going to concave up from 1 to 3. And during this time, from 1 to 2, we are still going to be decreasing. So it's going to form the base of this parabola in a way, because we're still concave up until 3. So you can only imagine that what's going to probably happen here is we're going to go up, right? And sure enough, since we are increasing from 2 to 4, that's exactly what's going to happen. Okay, so you know it's kind of going with the flow in a way, and you get it eventually. So now what happens from 3 to 4? Well, from 3 to 4, we are increasing, and we are now concave down. So we're going to go like this, right? And we're going to slow our increase. And then it looks like we're decreasing from 4 to infinity. So that is where this thing turns around, and we go back down. And that right there is your graph. Do we have a name for this function? Yeah, it's f. So y equals f of x. Okay? And that's really all it is. That's your graph. So it's just working in those different zones, seeing if you're increasing, decreasing, if you're concave up, concave down. Those are 2 things you check, and you just graph it out as you go. Okay? So that is going to do it for this video. I hope this video was able to help you, and we went over a lot of different stuff in this video. And so to get that all right in your head, I would really recommend going over that introduction that I did in the beginning of the video, that table where I talked about all this different information that we're finding, increasing, decreasing, concavity, inflection points, max and mins. Just getting that all right in your head and knowing what that looks like, what the tests are that go with it, that's going to be really helpful to you. Now, if you're interested in doing plenty more practice problems, which, you know, it's going to take quite a bit more to really get good at this stuff, definitely check out that full Calc 1 course in the description down below. Again, I go through all these practice problems, all these additional things with you. It's not just me giving you a worksheet and then saying, have at it, and that's it, right? It's not that. So if you're interested in that, check out the description, but that's going to do it for this video. I'll see you soon.